Today we're talking about control loops and how we use them in FRC to control the various aspects of our robot and get them under fine control, more so we can take some of the work off the drivers and have the robot do a lot of the work on its own. It can be it has a lot more fine control when it's using sensors and things than when we are asking the driver to do everything or the operator to do everything on the robot. So let's talk about how we do that. So the very important part of how we do that is what we call feedback. And feedback is when we use sensors to get actual information about what the robot's doing or about the world that the robot's interacting with. If we don't have sensors, we don't have feedback. If we're not able to know how far a motor spun or how high the elevator is, or anything like that, we don't have feedback. And then we don't have control loops operating if we don't have that feedback. That's one of the really important parts of this, is that we're always doing stuff based on what the sensors are telling us. So we do give instructions, so we're still telling it what to do, but the robot is basically able to check if it's actually doing that, and that's the important part. In FRC, the computer in this little model down here that we're looking through, so basically we give it a command, the computer does some math, it sends a command, basically it sends an output to the motor and the mechanism, and it tries to actually move and do the thing, and it has some sort of output that is measured. So say in like an elevator, we would tell the elevator to go up. The computer would figure out, okay, how do I tell it to go up? What do I need to do? The motor would actually move, would start turning. It would actually move the elevator up and down. We would have a sensor that's able to measure that and tell us how far the elevator has moved. It would report that back, and then the computer can do something with that information. So that's the basic idea of feedback. Feedback can be super simple. It can be something as easy as like this sensor could be a switch at the top of the elevator, and all it's doing is once the elevator is at the top of its travel, the robot stops telling it to go up, right? So that's a super basic feedback. Anywhere in the middle range, we're still relying on the driver to kind of move the robot around, move the elevator up and down. But it's still feedback if we know we can't go too far up or we can't go too far down. That's still some really basic feedback. The computer in this example could either be the RoboRio or a smart motor controller. So the Talon or the Talon SRX, the Falcon or the Talon FX that's on the back of the Falcon 500 motor, or the Spark Max that we were talking about last week and we're going to use in our examples today, could all be that smart motor controller that can handle some of the feedback on its own. Moving forward, so when we have feedback, or if we don't have feedback, let's start there first, we call that open loop control. So anytime where we're have some mechanism on the robot that isn't, its motion, its power, its speed to the motor, any of that isn't controlled by sensors, it's not looking at sensors, it doesn't know what's happening, it's just outputting some amount of voltage from the battery to the motor and doing something with it. So a lot of times those will be things that we don't really super care about how fast they're going. So things like our intake motors that are just trying to suck in the ball. We've already looked at how to program some of those. We've looked at some of the very basic code for that. And a lot of times we'll just have a single button where when you push it, we tell the motor to go to 100% of its power or 80% of its power, right? We send it 1.0 or 0.8. Anything like that. If we want to reverse, we send it some negative number, but we don't actually know if the motor is actually spinning up at some amount of RPM. We don't know really what it's doing. We just know we're outputting it and telling it to do it. We don't know if it's actually happening. And so that's open loop control. That's also called manual control. A lot of times we'll have backup modes or something. Maybe the feedback system on a robot isn't working, some sensor failed, some of the code went wrong or something. We'll have backup systems that the operator or driver can take over and get back into some sort of manual control. So that may be able to do enough with just manual to do something in the match in case something else isn't working. So a lot of times we'll still write manual or open loop control stuff, and we'll use it a lot of times for testing and for backup. But when ideally most of our systems are eventually going to get to what we call closed loop, which is when it's using that feedback throughout the process. And closed loop control normally implies a little bit more than just having some amount of feedback. It normally implies you continuously looking at your output and adjusting what the motor is doing based on the output. And so that's mostly what we're going to talk about today, is this closed loop control idea. Closed loop control requires that you have some sort of control loop, and the control loop is kind of the programmed part. It's the algorithm that we use to take the information from our sensor and then adjust our output accordingly. All right, so this is an example of an open loop system real fast, so you just have some comparison. In an open loop system, we don't have this bottom sensor part. So this goes away. The only thing we have is we tell the system or the robot to do something. So maybe it's to turn the intake on. The computer says, okay, you told me to turn it on. I'm going to command the motor to go on. The motor goes on and it has an output. And whatever that output is, nothing else can change it. It's just going to keep doing that until we give it some other command, no matter what. So this works for some things, like I already said. There's times where this is more than enough and doing anything else is just too complicated. But there's many times where this just is insufficient to be able to do things fast and reliable and quickly during a match. And so those are the times we move on to closed loop control, which gets a little bit more complicated. So instead of just telling it some voltage percentage like we did in open loop, our commands are a little bit more complicated. So in closed loop, we command the system to reach a set point or a command. Those terms get swapped around pretty interchangeably. So this might be commanding the elevator to move to 48 inches from the ground. So instead of just telling it to go up with some voltage and tell the motor to spin, we're telling it an exact height to go from the floor. And then this control loop and the computer, RoboRio, motor controller, whatever, is going to figure out when it's at that height, and then it's going to stop. So it's a lot more intelligent, and it allows us to do a lot more things reliably and more precise than if the drivers were just doing it manually. This also works for velocity control. So if we have a launcher wheel, like in our 2020 shooter, when we had to launch the ball into the goal, we would set that to very specific RPM. So we get a specific velocity. So every time that a ball goes through, it's basically, we're trying to make it go into the goal and land at the same point. If we didn't have this closed loop control for the launcher wheel velocity, each ball through might be going all over the place. Some may go high, some may go low. Even if you're kind of telling it to go at the same battery voltage, you don't actually know how fast it's spinning, because it'll slow down as one ball goes through it. It may not speed back up. The battery may just be low. The battery may be too high. You don't really have enough information to make a precise shot unless you use a closed loop control. What we're going to talk about from here forward, from basically all of our feedback, is using measuring motor revolutions with an encoder, or measuring the revolution of something with an encoder. The simplest one, and the one we use the most, like we talked about last week, is the encoders built into our brushless motor controllers. Since we have those now and there's an encoder in all of them, it's really easy for us to get those plugged into their smart motor controllers and use the control loops built into there to do this closed loop control on the motor controller itself. So then all we're doing is kind of tweaking these values. They have software already inside of them that lets them do the closed loop control, and we just have to tell it which ones to use and kind of tweak all the values to get it to do what we want. So this is a little bit tricky to understand, but I want to make sure this is clear because it sometimes gets confusing. The actual motor is still outputting, is still being controlled based on a percent of the battery, right? You're still telling it, it's still eventually going to get some amount of voltage. We just added some more math and some more computer power in between what the driver is telling it and what the motor is actually doing. So now the driver has some button that, instead of send motor to full forward or send motor to half speed, we now have a button that says send elevator to 48 inches, and the computer will control that. The computer can control that. We'll take that in and say, okay, I want to go to 48 inches. I can use the information from my sensor, and I'm going to figure out how fast to tell my motor to go for it to get to that speed. And we're going to talk about what that formula is and how we figure that out the rest of today. So that's what we're going to kind of dive into, is what is the computer actually doing to take our command, to take the information from the sensor and get us that output. That, like, basically it's figuring out what percentage of the battery, the actual amount of power to send to the motor all the time to get us to the output that we want. We had a question of when would control loops not work. So the control loop may not work if somehow a sensor failed. So maybe the sensor isn't reporting back information anymore. A wire came undone, something like that. There could have been a software problem. Maybe somebody updated the software incorrectly and we got a bad value somewhere, and now it's trying to do something, but it's not actually tuned in properly. So it's, instead of, we're telling it to go to 3000 RPM, and instead it's going to, like, it's going at max speed for some reason constantly. We could have a default manual control that lets us do a little bit of slowing it down or something, and we get something close, even though it's not as good as closed loop. For that single match, it might help us still score more points or something. Or especially if we just need to test and make sure something's working, we normally have a test mode of some sort as well. Okay, so the number that we tell them that we're commanding the system to go to is called the command or set point. And then the number coming back from the sensor is called the measurement. So this is the number that we're getting from the output. We have an encoder somewhere on the motor or on the output shaft somewhere, and it's telling us how far we've traveled, either in number of rotations that we can convert to something like inches, or it's telling us how fast we're spinning in RPM. And then those two numbers are what get used by the computer to figure out how fast the motor should go. So in this example, the elevator could currently be at 10 inches, or the launcher wheel could currently be at 0 RPM. And then when we tell it to do its commands, we can tell it to command to go to these spots. It would have to figure out how to get from where it currently is to where we want to be. It is very important to make sure that our measurements and our commands are in the same units. It would not work very well if you're coming back from the sensor and we're doing math and we're like, okay, we're at 40 millimeters and we want to go to 48 inches. We have to make sure that in our formula, we're doing those conversions and getting them to where we're able to compare them properly. It's very easy for someone to forget that step of the math and do the unit conversion. And then all sorts of things are going to mess up if you're in metric instead of standard. Then there's other types of different units and just choosing different things. So you could, in theory, be in revolutions per second if you wanted. There's things that use like encoder ticks per 10th of second or something. Like, there's all sorts of units you could be in. So you always want to make sure you're kind of matching those up and getting them right before you're doing the math. And it's just something to think about. Most of the time it's done for us, but on occasion, if something's just not working at all, that may be a place to look to figure out why it's not working. Okay, so what we call the difference between our command and our measurement is called error. And error is incredibly important to control loops. It's very, very simple. It's just subtraction. There's nothing really complicated about it. But the concept allows us to do a lot. So like I said, error equals command minus measurement. So in the examples that we've given so far, our current error, if we're right at the beginning of our process and the elevator is sitting 10 inches from the floor and we want it to go to 48, our error is 38 inches. So the difference between command and measurement is 38 inches. So this number is basically the number that we'll use in a formula to figure out what our output to the motor should be. In the other example for launcher, the launcher wheel isn't spinning at all. It's sitting at 0 RPM. We want it to be spinning at 3000 RPM. So then that error is 3000 RPM at the very beginning. And I think it's important to understand that this control loop is constantly happening. So it's not something that just happens right at the beginning when we like put in the command. We tell it to go to 48. It starts figuring out our error. It figures out the motor output. It does something. It checks how far it went. So maybe it's now at 47, or now maybe it started at 10. Maybe now it's at 14. And then so 14 will come in. We'll get a new error. We'll do 48 minus 14. We'll have 34 as the error. It'll do some more calculations and it'll get a new output for the motor. And it'll keep doing that over and over again the entire time we're telling the control loop to run. And so this is how it's able to get us to the position we want to be at, or the position or the velocity we want to be at, because it's constantly checking our output, using that sensor, getting a new measurement, feeding it into the math that the computer is doing, and then getting a new output for the motor, and just doing that loop over and over and over again. That's why it's called a control loop, because this is just happening constantly. After we give it the first command, it's just constantly doing that. There are times the driver can update the command. So maybe we don't want to be at 48 anymore. Maybe we want to be higher or lower, whatever. The driver can update that, and that new input goes into the math, and it keeps doing the same math over and over again to get that motor output, and constantly update it so we can have the robot basically do what we want, do it smoothly and reliably without the driver just constantly trying to update things and move the joysticks and things like that. Many of the kind of basic control loops rely solely on error, so it's definitely important to understand what we're doing. A lot of our math from here on out we'll refer to error. Just remember it's command minus measurement, nothing complicated. Okay, so we're gonna look at this elevator example for a little while. And this is a really basic elevator. This green block is on our robot. It's able to move up and down on these side rails. It starts at 10 inches and it's able to raise all the way to the top at 48 inches. Right, and we have a couple states of where it could be. So we have A is at the very beginning, it's sitting at 10. B, it rises up and it's about a little close to halfway through, it's at 30. Here we're at 46 inches, and then at the very end we're at 48. So if we know we're commanding it to go 48 inches, we know all of our current positions in each of these states, we can figure out what our error is just by doing that basic subtraction. So if we do that subtraction, we get that the error for A is 38 inches, right? Because we do 48 minus 10. For B, we do 48 minus 30 and get 18. For C, we do 48 minus 46 and get 2. And for D, we do 48 minus 48 and we get 0. So you can see from A to D, the error is getting smaller, right? We're approaching our set point. We're approaching our command. So then the measurement gets bigger and the error gets smaller as we're going up this, or as we go from A to D. Okay, so again, the system is controlling for position. It's trying to move the elevator to a certain position. But again, all we can really do is command the power of the motor, which controls velocity, right? We can't there's no specific way to just tell the motor with the motors that we use to like move half a rotation or something, right? Like all of it is, we're always outputting a voltage, which gets converted to a velocity inside the motor. Or it really just moves the motor, right? Some amount of power or electricity is spinning through the motor to move it. So we kind of need to know how fast do we want the motor to be moving relatively to each other in these positions. So kind of intuitively and just thinking about it in your head, should the elevator be moving faster at time A over here when we've just told it that our command is 48? Or should it be moving faster at D over here when the elevator is at the very top at 48? This should be pretty obvious that we want A to be moving faster since it has a longer way to go. It has to go all the way to the top. And at D, it shouldn't be moving at all. It's finished. It's at 48. That's where we told it to go. So we don't want the elevator moving at all if we're at the top. Or if we're at the point, if we're at our command point, if we're at our set point. We do not want the elevator to be moving, so it should be stationary. So it should be going quite a lot slower than it is at A when it's just starting to move up all the way to the top. We should be telling A to go the fastest because it has the longest way to go. Similar question, but a little bit trickier. Should the elevator be moving faster at time B or time C? So here we do have to think a little bit, but it kind of the same reasoning that as the elevator basically should be moving faster at B because it still has about half of its travel left to go. But at C, it should be slowing down because ideally we were trying to get it ready to stop by the time it gets to D, right? It's only 2 inches away. If it's moving at full speed here, it's very likely going to go past it or run into like this bar really hard if it can't go anywhere. Okay. Yeah, sorry if the font's a little confusing. This is 46. This is 48. We had a question in chat. Okay, so so this is slowing down as it's going from 46 to 48. We want it to be slowing down. So it's going to be going faster at B than it is at C. And simplified idea, there's times where you may want this to be a little bit different. We're not going to get into that today. But in general here, we want A to be going the quickest, then B, then C, and then D to basically be 0. So we want C to be slightly faster than D, but not very fast. And then we want A and B to be definitely faster than both of C and D. So then the question is, okay, we have this error idea. We kind of know a relation for these speeds. How do we make this equation that we can put into the computer that allows it to react in the way that we're talking about? How do we make it so that at A, it's going the fastest, at D, it stops, and that it basically slows down through B and C? Turns out there's a pretty simple way to do it. It doesn't take much math at all. And the way we do it is it's called a proportional control loop. It probably sounds way more complicated than it actually is. Proportional in math means that it's just a constant ratio to another quantity. So it's literally just multiplication. So it's nothing that all of you have done multiplication before. It's nothing complicated. So we just have to make an equation just like you would in algebra or anything like that, that takes error. So we know what error is. We know error is command minus measurement. And we're going to output a velocity that gets smaller as error gets smaller. So our equation ends up just being error times this thing we're going to call Kp, which is our proportional constant. The constant term is a little confusing sometimes for people. It's not like a chemistry constant where it's something where it will never change. It's not like a known quantity in the universe. The constants that we're referring to are only constants in the sense that while this is like this kind of loop is running, it doesn't change, right? The command might change. We might tell the elevator to go to some other point. The measurement from the sensor is definitely going to change because the elevator is going to be moving. So the sensor measurement's definitely going to change. So that means our error is going to be changing. But this Kp, we basically this is what we set. We'll set this before, kind of while we're programming, we'll set this to be some value, and we may modify it while we're programming, kind of getting the system running. But ideally, we're not changing this very often during an event. We're definitely not changing it like mid-match. So in that case, it's constant kind of compared to error is. We are allowed to change it, so it's not like a permanent number, but it's more constant than error is, just kind of in this loop that's happening all the time during the match. This value doesn't change. Okay, so looking at our elevators again, we have to figure out what Kp do we actually want. So we have a whole host of, we basically are able to set up these equations where these values over here are the error at each of these timestamps, right? Remember, error is command minus measurement. So 48 minus 10 gets us 38. We kind of did all that already. And we know Kp is going to be constant. So these are going to be the same value for all of these stages. We're not going to be moving KP just because the elevator gets closer to its set point. We're not going to be changing up KP. So then figuring out what KP is and like adjusting it is what we call tuning the control loop. So when we tune these constant values and we modify those numbers a little bit, that's what we're doing when we're tuning the control loop and making it perform slightly better. And there's eventually we may have a couple different constants that we use in an equation, and so you can change different ones, and they have slightly different effects on the actual output of the system. And because of that, there's sometimes you have to modify them in different ways. And so that process of changing these values is what we call tuning the control loop. And that's it's actually a lot of what we do to make them work well is this kind of tuning time. A lot of it is just sort of experimenting with it, seeing what happens if you make it a little higher, make it a little lower, what does it do? And then there's some other strategies and things involved in that we'll go into later. But this process of just kind of choosing this KP is pretty important. Okay, so there's some things we kind of know, right? So if this is the entire equation for output, so this equals thing is going to be how much power we're going to send the motor. So if we send it 1, it's going to go full speed. If we send it 0, it's going to stop. So there are some things we kind of already know, and we can kind of, based on what we actually want the elevator to be doing, we can plug in some numbers to some of the other sides of this equation, so we can start trying to like solve for a KP that makes sense. The simplest way to do that is at D, when it's at the very top, when it's reached its set point, we know that we want this output to be 0, right? That would make sense. It's at the position we want it to be in. We want it to stop. The way we tell the motor to stop is we give it an output of 0. So then this equation has to equal to 0. Luckily, if error is 0, you multiply that times KP. No matter what KP is, this is always going to be 0 because 0 times anything is 0. So we're good there. So this D case just works now. So then we have to figure out, okay, so then what is KP for these other 3? One way for us to solve that is if we know A is supposed to be the fastest, we can tell A to be the full speed of the motor. So A can be 1, which is as fast as the motor can go. And then we can solve that equation of 38 times KP equals 1 to let us get an idea of where to start with KP for our tuning. So to solve that, if you have this 38 times KP, you would just do, right, we can do some solving in algebra, nothing too hard. You just bring 38 to the other side and you get 1 over 38. And that's what the value is, 0.0263. And if we plug that in for KP here, those are the 2 outputs that we get for our other 2 values. So basically what this is saying is right at the beginning, it would be going as fast as we can. It would start slowing down to about 30. It's going a little under half speed. And then by 46, it's going, what, 2/100ths of its max speed, or like 2.5 somewhere in there, 2.6. So it's getting really slow at C, which is what we want. It's getting slower at B, which is good, and at A, it's at full speed. So that's reasonable. That's not terrible. It's meeting the requirements that we said before. But those requirements may not always be exactly what you want. So one of the issues with this setup, especially maybe you have a bigger elevator, maybe instead of your elevator only having this like 38 inches of travel where it can go from 10 to 48, maybe you have a much taller elevator and it's going from 10 to 96 or some other really tall game. We had games where we've had to reach up to 8, 9, 10 feet in the air before. You probably don't want your elevator slowing down as soon as it starts moving, or if it has to move anything else from the very max movement, it would never actually reach its top speed. Maybe that's not what you want. So if we want to change when we want it to slow down, so maybe we only want it to start slowing down once it reaches an error of 18. So that's this middle B column, right? So from A to B, we want it to be full speed. And then from B through D, we want it to slow down and then stop at D. How do we do that, right? That equation gets a little bit more, that gets a little bit different. So we can do the same thing we did, but instead of the 1 up here, we'll put the 1 in the 18 or in the B column. And so now KP is 1 over 18. It's this number 0.05 repeating. Rounding at some point is always fine, by the way. We never use the repeating things. I think we can only do 4 decimals with the rev system, and that's fine. Anything after, you just can tune up or down, and it makes it okay. Oh, did I not change something? Someone is commenting that I did math wrong, which is very possible. No. Oh, did I do? Oh, I did math wrong here. Okay, I understand. Yeah, this should be 0.052. That makes sense. That was just a typo. Okay, so math is good through here, and that's where we need it now, so we're okay. All right, back to this problem. So B is equal to 1 now, so we're good there. We know that it's going full speed at B. It'll start slowing down as soon as this number gets below 18, because anything else, like as soon as it's 17, it'll be 17 over 18, so it'll be less than 1, and it'll start slowing down. So from B to D, we're pretty okay. But at A, we have this problem that we're trying to tell the motor to go to 2.11, which is not possible. We can't tell the motor to go to 200% of the battery voltage. That's not something our system allows us to do. 1 is the max speed we can send the motor. So because of that, what we do is we set a max output in the code in the program for the motor output, basically. So it'll turn any output over 1.0 to 1.0. So a simple line of code that could do that is something like if output is greater than 1.0, output equals 1.0. So that really simple logic just kind of caps the motor value. Many of the smart motor controllers, like the Spark Max, will have a setting for us to do that. So we'll be able to set the max output just in a setting, and it kind of does this, it does the limiting for us, where it limits how much of a max output can be. Right, so now instead of that being 2.11, it's now set to 1 before, and we get kind of that motion profile, or we get that the motion output that we want, which is 1 all the way until it reaches that 18 inches, and then it starts slowing down. So we're good there. There's also times where we may not actually want the output to ever be full speed. Maybe 1.0 is just too much. Maybe it starts up too fast and it like jerks, which we'll actually see in a second when we start doing the live demo. So we can use that same max value to constrain the max speed even more. So instead of 1, we could set it to 0.5, and now it'll just use 0.5 through here. Even though it's trying to tell it to go to 1, it'll just use 0.5, and then it won't slow down until the commanded output is less than 0.5, and then it'll start slowing down. So you can kind of consider what that would do to the speed and kind of how you would change that. But that's one way that we can limit how much power the mechanism, whatever we're doing, has, is just by setting that max value. We'll actually deal with this question later because I don't think I actually solved that. So ignore that for a little bit. That's another day. I realized that was going to be too complicated for what we're doing today. Okay, so let's actually switch over and look at the position example in the live example. So portion of screen. Okay. All right, so we have our SparkMax running again with our Neo here. And we have our Rev SparkMax client over on this side. Let me change some things. I was testing some stuff before we got into this. We don't need that. We do need this. Okay. All right, so we're gonna have a an output. The pink line is going to be our motor's position, so between 0 and 50. And this red line is going to be our motor's output in terms of battery voltage. So it's going to go between -1 and 1, just like our motor can always do. So we'll graph two different lines as we do it. We're going to tell it that we want our motor to be in position control mode, because that's what we're trying to do. We want this to turn a certain number of positions. All right, so looking at this, we should be able to put this value in for our KP, this 0.055 value. Let me erase that one. We don't need that yet. We'll look at that in just a second. 0.055. This thing gets a little weird. Why is it? Okay. I think it does 4 decimals. All right, so we can go to there. So that's where we kind of started with. Over here we have our limits. We're gonna actually, I tested this earlier and it was doing, in the setup I don't think I have enough power to let it run at full speed. So we're actually gonna start it at max output of half speed. And that seemed to work better with our graph, which is my testing. On a normal robot, we would be able to do it at 1, but I don't have it actually running off a battery. I have it running off of a wall adapter. Okay, so we should be able to see the graph starting from 0, because the motor hasn't moved at all. I think. I don't actually know if that's true. Let me run it to 0 real fast. See, that's the problem. So it moved a ways. I was testing other things and it kept the encoder value. I actually don't know how long this is going to take. I may have to just clear it. Unexpected. Okay, well, the motor is just spinning. Is it working? All right, there it goes. Okay, it was just really far away from 0 because I was doing velocity with it, which we're going to do in a second. Now it's all back. All right, so it's starting at 0 and it's the output is nice at 0. We're going to move this up and tell it to go to 48. So we're basically going to start at 0, tell it to go to 48 and see what happens. So it did that relatively nicely. So we have this graph. It started at 0, the position went up, and then it kind of curves off as it starts slowing down, and it reaches somewhere close to 48. It doesn't quite make it there. So that's one of the things that we were that we'll discuss a little bit later of how to try to get it close. But also, this may be close enough, right? If our only goal is to get a ball into a goal, say like in the 2019 game when we had to have that elevator move the rocket up and down, or move the ball and push it into the different slots in the rocket. If we're off by, what is that, under or just around 1/4 of an inch or so, 1/8 of an inch or so actually, that's not going to affect our game piece placement. We'll be able to still put the ball in and we'd be totally fine. So you're totally fine in having some amount of error most of the time. You don't need it to get exactly to the right spot in most things that we're doing in FRC. And you can change that a little bit and build that into your system, and decide basically when is good enough. And so here, this 47.83 is totally fine for what we're doing. We can kind of see a graph there. We can zoom in a little bit more to make that graph a little bit more reasonable. Did I actually do it? Okay, let me try that again. We'll send it back to 0. All right. We can actually even make that smaller, it looks like. Let's do like 3 and try that. Okay. We'll send it back to 48. All right, so now we can see it a little bit. We can see that it's accelerating. The applied output didn't go quite straight to 5.0. There may be some stuff in the Spark Max controller that doesn't make it be instantaneous, but it's, oh no, I think it's just that's just the timestamp, I think. Yeah, that's just how fast it can move. So the only reason that this isn't a straight up and down line is that it's only sampling so often, right? So it's basically just saying in the shortest amount of time possible, it went from not moving to going its max speed, which we told it to be 0.5. So this is basically an up and down line, but we can only see it for a certain amount of timestamp. So it's this small of an increment down here. I don't even know if that's actually what it's graphed at. But that's the rough idea. So it's pretty much instantaneously going to full speed. Sometime around sometime around position 41 or so, it starts slowing down, and then it gets slower and slower as it reaches its max position at 48. So we can change the it still should be able to do that basically for other positions that we didn't necessarily command it for. So maybe we're at 48 and we need to only go down to about halfway. Say we want to go to 24. Ooh, maybe. Okay, so you want to go to 24 from there. It'll still be able to do that. It'll just do it a little bit differently, right? It was just at speed for a little bit shorter, but that error was still the same amount. So it's still able to make this like smooth part of the graph come down here to get us to the spot that we wanted to. And it was doing all of that negative because it was going backwards, right? And so all of that math still works for us since it was, since if we flip if the command point is less than our current measurement, we'll get a negative value. So the motor will output negative, and the equation just sort of works and does what we want it to do. Okay, so looking back real fast, we're gonna flip back to just the presentation. Okay, so let's look at the velocity example as our last example of the day. So the launcher wheel, instead of controlling for position, we're trying to control the velocity of the wheel. How fast is it spinning? And you can imagine that's going to be a little bit different, right? So in this diagram, this one is a little bit harder to tell because we don't just have heights. So these are the current velocities at each of these timestamps. So at the very beginning, the wheel's not spinning at all. At B, it's spinning at 1500 RPM. At C, it's spinning at 2800 RPM. At D, it's spinning at 3000 RPM. We're commanding it to go 3000 RPM. So then if we figure out the error at each spot, error again is just command point minus measurement. So 3000 minus 0 is 3000. I get 1500, 200, 0. Again, that math isn't that hard. So now we have our errors. And so we can attempt to do the same KP calculation that we did before. But the assumptions are a little bit harder to deal with in this equation when we're doing velocity. Because before, when we had this 0 down here, because that's where the elevator was at position, we didn't want it to move anymore. We tell it to be 0 output, and that's great. However, when the launcher wheel is at 3000 RPM, we don't really want it to stop outputting, right? We don't want it to stop moving. That doesn't really work for us. We want it to maintain that 3000 RPM. So our output should only be 0 when we actually want it to stop spinning. And none of these points, since we're telling it to go 3000 RPM, we never want it to stop spinning. So none of these equations, or the equation that we're actually going to use, should ever be 0. And that's a problem because our error eventually gets to 0. Right? 3000 minus 3000 is 0. So if we only use this KP proportional control method, we'll always have this like 0 here, and that'll just be a problem. So we have to introduce a new term to help us fight that. And the new term is basically just we basically just add another bit of multiplication in this example. So the new term that we're adding in is what's called feed forward. So at the very beginning of today's presentation, we talked about feedback. Feed forward is not quite the opposite. Like I definitely don't want to do that. It's just it's a thing that we add in to our feedback system that allows us to sort of predict a little bit more about how we want the output to behave. So instead of reacting to the error in the system, instead of reacting to the measurement that we're getting from the sensor, it only reacts to the set point or the command. So however fast we're telling the wheel to spin, it's basically like a KP, but only on the set point. And so we call it KF. And it's basically in our velocity loop and in other loops where this is the same idea, it's there to help maintain that velocity. And we can kind of predict, okay, we know enough about our motors and our system to say at D, we need the motor to have this much output to be able to maintain 3000 RPM. So then 3000 times KF will kind of equal that, since this term is going to be 0. We're able to predict that output. So if these are the kind of rough values that we want, so if roughly we think to spin at 3000 RPM, we need the motor to spin about 50% of its power output from the battery. We know it's about this much. And then if the anything else, we'll use the KP to adjust for. Because maybe it gets close, but it never quite hits the exact command point. That'll be okay. We'll make it, again, we don't necessarily need it to hit exactly 3000 RPM. Sometimes it's going to hit 2950 or something. It'll stay about there. And that's probably good enough for us. As long as we kind of know and make it repeatable, we're pretty okay. Sometimes you can get it exactly right too. It just takes more tuning and adjusting. But a lot of times you don't necessarily need it exactly right. You just need it to be repeatable, so the ball goes in the goal and you know what that velocity is and what that set point needs to be. Okay, so figuring out these are, again, a little bit trickier. We have two different constants now, so it's not as easy. But because we have this one down here where this term equals 0, it's a little bit easier, because 0 RPM times KP is always going to be 0. So then we can kind of just solve for this one on this side. The example for this, which we'll try to do, it's a little bit wonky. We can show it doing speed control, but the numbers don't quite work here. The interface doesn't let me put in anything past the 4th decimal, so these aren't going to be exact. And just doing speed control on a motor alone that doesn't have a mass gets a little tricky. It's able to accelerate to a speed very, very quickly because it doesn't have to spin anything up. So you don't really see the curve as well. So I'll try to get a better example in the future. We may be able to do it on our actual 2020 robot, and we can see it, how the launcher wheel spins up a little bit more when it's actually having to spin up a heavier wheel that takes longer to get up to velocity. But this is the rough idea. So we can calculate a KF from this equation. Again, nothing too hard. Multiplication, division, add, subtract. And so we can plug everything in to our setup, and we can start figuring out, we figured out what KF was, we need to figure out what KP is. If we wanted this to equal 1, it ends up being that this KP and KF are the same here because they're both 3000. They wouldn't have to work out that way. And for this setup, you'll see that it doesn't quite work out that way when we actually tune it, because a lot of times our numbers are going to change from our kind of base calculations, especially when once you have a lot of mass and other things involved, none of that's being brought in to these equations right now. We don't have any of the physics in here. We don't have a model for that in this yet. There are people who do that. There's people who try to model a lot more of the actual physics of what's going on. It gets a little bit more complicated, but you can kind of determine these values based on that if you do a little bit more math. But a lot of times we'll just get to a number that's relatively close and tweak it to get to right, depending on how important the system is and if it's behaving the way we want it to or not. Okay, so let's go back and let's see if we can do velocity control. I don't know how well it's going to work without more of a mass, but we should be able to get close. All right. Okay, so we're going to switch it up in here to tell us that we're no longer showing position and we're showing velocity. I'm going to have it be from 0 to, let's say, 4,000. We'll keep motor output. We'll swap this to velocity control. These will change, right? Because these get a lot smaller. So we get, it's doing the thing where it's making me angry. All right, there we go. Okay, so let's start somewhere about here. This is just it rounded down with a KP and a KF. If we tell it to try to go to 3,000, it doesn't quite get there. So it only gets to 2205. So it actually kind of went up, it went over, and then it brought back down. And this is kind of where the KF kept it to. Since we only have this 0.1, it was able to kind of steady state out at that sort of value. We can tweak it a little bit and see if we can get it closer. So I can double KF and see what happens. So that should make it go quite a bit faster. Remember, we do have K output max set at 0.5 still. If I don't, the motor just spins up really fast and it tries to jump out of my hand. We can go ahead and run it here and see what happens. So now it got up to 2908, but it was just at full speed that whole time. So at voltage, we can see right in the graph that it's going to 0.5. So it was trying to go faster, but we weren't letting it. So we can up this a little bit if we want, and we can see what it'll do. So if we tell it that it can go to 0.6 now, we can tweak it again and see what happens if we run that. So this time it went a little bit past 3,000 and it came back down to 3,308 while outputting a little bit under 0.6. So it stopped going full speed, but it definitely wasn't quite there. So there may be some things we can try to do. Well, let me get a fifth. Oh, it'll let me get a fifth. So maybe I can actually get this to the right value. Let's see. It wasn't letting me earlier, but maybe it will now. All right, let's see what it works now. Well, so that wasn't happy at all. My guess is it did not like the extra decimal point. I think it only lets me do 4. Let's see if we can. Oh yeah, and then it got an error when we sent something, so I don't know what it's doing. This is one of the problems with this format. It doesn't always like some of these smaller numbers. Yeah, so it went under. It's going under its max value, but it's not quite settling in at 3. So sometimes there's things we can do in our actual, a little bit more that we can do in code, and once we have the full mass on it and things, and it makes it harder to spin, it's a lot easier to tune to an exact speed. Because these numbers have to be so small right now for this that it makes it a little trickier. I don't think this lets it do anything different. Yeah, it just cuts it out once that number is too small. Okay. Oh yeah, no matter what it does that. That's interesting. Okay, so Yeah, the example didn't run as well as I would have liked, but we may be able to get this set up in a little bit nicer way so we can see velocity control. But the concepts from the slide should all be there, and those all work and are correct. But KP and KF are two of the most useful ones. KF and KP when we're trying to do velocity, and just KP when we are trying to do position. And you can do a lot with just those settings. We'll discuss some of the other ones in future presentations. There's some more advanced ones that we use sometimes in FRC, but not nearly as often as we use proportional and feed forward. And then there's also some more advanced control loops and things that add on to these basically to make them a little bit easier to get your systems up and running and faster. But these are kind of the foundational elements of what we need to do in FRC. All right.